Hello students, in this video we are going to derive an expression for acceleration due to gravity on the surface of the earth. We all know that when a body is falling freely, its velocity increases with respect to time, and you know that the increase in velocity or decrease in velocity is nothing but acceleration. And here the freely falling body is accelerating, and the reason for this acceleration in that freely falling body is Earth's gravitational force or Earth's gravitational pull. And therefore the acceleration produced in a freely falling body under the effect of Earth's gravity is called acceleration due to gravity g. And in this video we are going to derive an expression for this acceleration due to gravity g. So to derive this acceleration due to gravity, let's consider a body of mass m on the surface. Consider a body of mass m on the surface of the earth of mass capital M and radius capital R. So here we are considering a body of mass m on the surface of the earth. So this body's mass is small m and it is on the surface of the earth. And here the mass of the earth is capital M and its radius is going to be r. Its radius is capital R. And now using Newton's law of gravitation, the gravitational force between the earth and the body m is the gravitational force. The gravitational force between the earth and the body is. So here we are going to use the Newton's law of gravitation, and the force is F equals to capital G capital M into small m, because it is product of masses and inversely proportional to the square of the distance between them, that is r square. So there is a common doubt here, that is earth and body both are in contact with each other, and then how come the distance between them is capital R, that is the radius of the earth? Because you already know that the earth exerts force on this body as if whole mass of the earth is concentrated at the center, because here we are considering earth as a uniform spherical object, uniform spherical body, and because of this consideration, or that's how this gravitational force works, that's how this earth exerts gravitational force on this body whose mass is small m, and because of that only the distance between the center of the earth and the body is capital R. Okay, so that's why the distance between the body and the earth is going to be R, and that's why it is divided by r square, and we call it as equation number 1. And this gives the gravitational force of attraction between the earth and the body. And now the weight of the body, the weight that we measure, that weight of the body, the weight of the body on the surface of the earth is, the weight is given by F equals to m into g, and we call it as equation number 2. So you know that this weight is provided by the gravitational force only. The weight is nothing but the gravitational force on the object, and therefore the weight is equals to the gravitational force. And from equation 1 and 2, from equation 1 and 2, this mg is equals to capital G capital M and yes small m divided by r square, So m is present on the both side of the equation, so it is going to cancel, and therefore the acceleration due to gravity on the surface of the earth is small g equals to capital G capital M divided by r square. So this gives acceleration of the body. Okay, so this expression is acceleration due to gravity of the body on the surface of the earth. And when you observe this equation carefully, it is very clear that this g is independent of the mass of the body, because there is no term small m here, and this g only depends on mass of the earth and radius of the earth. And if you are considering some other planet, then the acceleration due to gravity of that planet depends only on mass of the earth and inversely depends on the radius of that planet, mass of the planet and radius of the planet. Okay, yes, this is the acceleration due to gravity on the surface of the earth. And from this equation it is very clear that the acceleration due to gravity is minimum at the equatorial region and maximum at the polar region, and that is because of this value of r. So r is maximum when it is at the equatorial. When you consider the radius of equatorial region, the radius is more, and at the polar region the radius is less, and the difference is 21 kilometers. Equatorial radius is more than polar radius by 21 kilometers. So that's why at the polar region the acceleration due to gravity is maximum, and on the equatorial region the acceleration due to gravity is minimum. Okay, yes. Now we are going to express this acceleration due to gravity in terms of density of the earth. Acceleration due to gravity in terms of density of the earth. Density of the earth, and that is rho. Density of the earth, and that is represented as rho. Okay, you know the formula for density. Density equals to mass by volume, and using that formula the mass of the earth will be, mass of the earth is equals to, you know that obviously mass equals to volume into density. Okay, so it is mass of the earth equals to volume of the earth and into density of the earth, into density of the earth. Okay, so mass of the earth is capital M, volume of the earth is V, into rho is density of the earth. And here volume of the earth, so volume, the shape of the earth is considered as a spherical, and that's why the volume of a spherical shape is given by 4 by 3 pi r cube, where r is radius of the earth, and this equation gives mass of the earth in terms of density of the earth. Okay, this equation gives mass of the earth in terms of the density of the earth. Okay, and now substituting the value of m in equation number 3. Substituting the value of m in equation number 3, and then we are going to get g equals to capital G. What is m? M is 4 by 3 pi r cube into rho, and that is divided by r square. Okay, and here this r square and this cube will cancel, and the remaining term for acceleration due to gravity is g equals to capital G. Okay, I will write first 4 by 3, so it is 4 by 3 pi capital G capital R into rho. So this gives us the acceleration due to gravity in terms of density of the earth.